So now we've just seen an illustrative example of osmotic pressure and how water moves as a result of that. Let's step back and define some terms before we move forward and get a more detailed picture of osmotic pressure. So we'll start with units of measure. A mole is a really simple concept, but I think people get confused. And a mole is just a quantity. It's just a number. And more proper definition is typed up right here. And it's a mole is the number of elemental entities as there are atoms in 12 grams of carbon-12. Well, 12 grams of carbon-12 has 6.02 times 10 to the 23rd atoms. 6.02 times 10 to the 23rd is Avogadro's number. And so we see that if we're talking about a mole of glucose, for example, then we are talking about a mole of glucose has the same number of entities as there are atoms in 12 grams of carbon-12. Well, then a mole of glucose has 6.02 times 10 to the 23rd molecules. And an equivalent way of talking about mole is a mole is a quantity of a substance whose weight in grams per mole is equal to molecular weight. So grams per mole, which mass over mole equals its molecular weight. Well, we just saw that 12 grams of 12 grams of carbon-12, 12 grams, is 1 mole of carbon-12. So this equals carbon-12 has 12 atomic mass units. This is just a way of accounting for each atom and its weight. So if you take a mole of glucose and you add all of its atoms together, then you find that it has an atomic molecular weight of 180 atomic units. And then 1 mole of glucose then has 180 grams. So it's a very simple concept. There's two ways of thinking about it. This is number of atoms there are, or it's weight. And so it's very simple. Molarity on that is just another way of defining a concentration. So mole is just a number. Molarity is a concentration. It's just molarity equals moles per liter. Is a volume. It's a volume of solution. Equivalence is also a similar concept. It's equivalence equals moles times valence. Valence is just the number of charge. So a monovalent ion, such as sodium, has only 1 charge. So 1 mole of sodium times 1, so 1 times 1 equals 1 equivalent. If we had calcium, this is 1 mole of calcium times 2, because there's 2 charges, equals 2 equivalents. So you could also see how this is, so you can see the difference between molarity and equivalence. Molarity is mass concentration we're measuring, and equivalence, if we divide by L, equivalence per liter is moles per liter times valence. So this is molarity times valence. So we're measuring charge concentration. Oops. charge concentration. An osmol, an osmol is just simply the number of dissolved particles. I just mentioned that osmol is the number of dissolved particles. To illustrate the point further, I'm going to draw some pictures that maybe will help explain the concept further. And so really, if you take one particle and it breaks apart into many particles, then you have for one particle you have many dissolved particles. So it's not just the number of things you put in, but it's how many things dissolve. So if, for example, we had an orange and we put one orange, this is a peeled orange. Oh, this is not orange. So we had one orange and it's not peeled, and we put it in the water and it doesn't break apart. So one orange leads to one dissolved particle. Now if we had a peeled orange and you put it in the water and it breaks apart into four slices, then one orange leads to four dissolved particles. So similarly, if you had 1 mole of sodium chloride, which is just salt, and you put it in water and it breaks apart into sodium ions and chloride ions, you have two particles dissolved. So 1 mole of sodium chloride leads to 2 osmoles. And you could see that if you have 2 osmoles, that has a greater contributions to osmotic pressure than one particle. So for 1 mole of sodium chloride, we're not just getting one particle contributing to osmotic pressure, but we're getting 2 particles. So that's an important concept. And here we have osmolarity and osmolality. Osmolarity is simply they're both describe concentration of osmol. And so osmolarity is osmol osmoles per liter. You remember R and R. And osmolality is osmoles per kilogram of solvent. Usually this is just water. So if you remember those are two reoccurring terms we'll see later on, more often. So we're ready to talk about osmotic pressure, and it's really a meat and potato idea in much of physiology. So let's try to cook it well. And over here we have an equation called Van Hoff's equation, and it really describes a linear equation between osmolarity and osmotic pressure. This term right here is osmotic pressure, and this term right here is osmolarity. So we can see this because G is really just the number of osmoles per mole. So we saw 1 mole of sodium chloride leads to gives to 2 osmoles. In a similar fashion, C is just a concentration. It's just molarity. It's just moles per liter. So if we had 1 mole of sodium chloride, 1 moles per liter, times 2 osmoles per 1 mole of sodium chloride. You see that moles cancel out, and this leads to 2 osmoles per liter, which is osmolarity. So osmolarity is linearly associated with osmotic pressure. And R is just a gas constant and it's 0.082 liters atmosphere over moles per Kelvin, and T is measured as temperature in Kelvin.